Modern civilization runs on a technology most people never think about. Not computers, not the internet, not global supply chains. Concrete. If it suddenly vanished tomorrow, the modern world would become physically impossible. We live in an era where we carry artificial intelligence in our pockets and Land Rovers on Mars, yet the physical infrastructure of our cities, our roads, skyscrapers, dams, and tunnels, still depends on a material technology revolutionized in the 19th century: Portland cement. Despite decades of material science breakthroughs, humanity still cannot move on from concrete. Understanding why requires looking past its dull gray surface, because the story of concrete is not really about a rock. It is about a brilliantly engineered solution to a massive logistical problem. For thousands of years, humans built with whatever they could carve, cut, or stack. Timber, clay, and brick worked, but they had severe limits. Building massive, complex structures out of traditional materials was slow, labor-intensive, and structurally constrained. Concrete completely changed the equation. By mixing rock, sand, water, and cement, engineers weren't just assembling a building, they were triggering a chemical reaction. They could pour this liquid stone into any mold, shape it around complex geometries, and simply wait for it to cure into solid, load-bearing stone. When engineers realized they could embed steel inside this mixture to create reinforced concrete, they shattered previous limits. Cities stopped sprawling outward and started climbing upward. Construction became dramatically faster and far more scalable. It became the defining technology of modern urban development. But if it is just a highly effective 19th century material, why is it still the absolute default today? We now have engineered timber, advanced composites, and high-strength alloys. The challenge is not that alternatives do not exist. The challenge is that every alternative sacrifices something crucial. Steel is exceptionally strong, but expensive and heavily energy-intensive to produce. Engineered timber can reduce carbon emissions, but faces limits in supply, durability, and large-scale deployment. Advanced composites offer impressive performance, but remain far too costly for mass infrastructure. Each solves one problem. None solves all of them simultaneously. Replacing concrete is not a simple engineering problem. It is an economic problem, a manufacturing problem, and a massive logistical problem all at once. Concrete is deeply entrenched as the global industrial standard. The raw ingredients, limestone, rock, and sand, are geographically abundant. Almost every country on Earth has access to them. The manufacturing facilities exist on every continent, and construction crews globally understand exactly how to work with it. Because the scale of production is so massive, the cost of concrete is driven down to a level that no modern miracle material can compete with. We don't stick with concrete because we lack the knowledge to build with something else. We stick with it because nothing else can answer the world's structural needs at this price point and at this scale. And that scale is staggering. Concrete is not just widely used, it exists on a scale that is difficult to comprehend. Humanity pours enough concrete every year to reshape entire landscapes. Roads, ports, airports, apartment towers, bridges, dams, and tunnels. Virtually every major infrastructure project on Earth depends on it. In fact, concrete is often described as the world's most widely used man-made material. No other engineered material comes remotely close to this level of global deployment. But building an entire civilization on a single, massively scaled material comes with an invisible cost. Structurally, concrete is an engineering compromise. Materials like steel are far better at handling tensile stress, the force of being pulled apart, but concrete offers an exceptional balance between incredible compressive strength and rock-bottom pricing. That affordability, however, demands a massive environmental toll. Creating the cement that binds concrete together requires baking limestone at extreme temperatures. That single chemical process is responsible for roughly 7 to 8% of all global carbon dioxide emissions. Furthermore, the relentless global demand for concrete requires mining millions of tons of river sand and gravel, a process that is quietly altering aquatic ecosystems worldwide. As the global population grows, cities must expand. The demand for housing, roads, and infrastructure will only accelerate. And the cold logistical truth is that we currently have no alternative material that can match concrete's price, its production volume, and its global supply chain. Yet engineers are not standing still. Around the world, researchers are actively developing lower carbon cements, carbon capturing concrete, and new production methods designed to slash emissions. Some approaches focus on altering the fundamental chemistry of cement itself. Others attempt to trap carbon dioxide inside the concrete as it cures. The challenge is scale. Even the most promising innovations must compete with an industry that already produces tens of billions of tons of material every year. Inventing a better concrete is difficult. Replacing the global concrete industry is even harder. Concrete helped build the modern world. The uncomfortable reality is that the modern world still cannot function without it. And until we find a way to make it cleaner, every new city, road, bridge, and skyscraper will force humanity to confront the same question. How do you replace the foundation of civilization when civilization still depends on it?